Let's start. Okay, so I will start introducing the statistical learning theory. My idea today is basically defining the goals of the statistical learning theory. Afterwards, I will bring some math and some probability to explain it like in details and maybe show some examples, because I think that makes everything easier to understand. And then I will start a little bit about the formulation. That's interesting, but a little, of course, a little more, math, basically. Okay, to start the goals, the basic goal we have with the statistical learning theory is to prove supervised learning. So, supervised learning. So if we consider what Vapnik, this Russian guy who came up with the theory, was improving supervised learning. So everything I'm going to talk, it's useful to understand sample sizes, for example, to understand the space of admissible functions or bias of some sort of algorithm we are working with, and things like that. So at the beginning, I define how we can prove learning. So the basic idea that Vapnik had was to define a generalization term, and this generalization term helps us to understand how learning will happen. So a generalization is basically comparing the empirical risk or the risk in a given sample with the risk and the whole population, the whole distribution, basically. So this is the risk, which is called expected risk, right? The risk in a distribution, in a joint probability distribution. In that sense, I see this in a simple way with this example. For instance, consider we have like a bunch of students in a given classroom. So we decided to provide some books, a list of books, and they started learning from those books, and they were capable of somehow come up with a model F. That F, that classifier, that regression function, is basically a model to represent knowledge. So if they were capable of building up a model out of those books, they can test that model in the sample, but also outside of the sample. So this guy here is the same as testing in a given sample. This is the same as testing in real-world conditions. So, for example, I could have, people studying a subject, and when I decide to apply a test, I could define a test just based on that book I suggested for the students, so they could get like 10 out of 10, so that the error here would be 0. For example, they would perfectly hit the test, basically. So when we put them in another condition, in a real-world condition, when they have to apply the knowledge in other problems, other real problems, they could fail like miserably and have like an error equal to 1, for example. That would bring a final result equals to 1, and that's the case where we don't have generalization, but we had overfitting. So every time we have this situation, that numerically represents overfitting. So, in fact, we are not interested in that situation. We are much more interested in the situation where those students were capable of maybe mark like something like 0.9, so the error is like 0.1. And when we apply that knowledge, when they apply that knowledge in real world conditions, that error could be like 0.11, for example. It's not perfect, but it's not that bad. So when we measure generalization here, it's going to be 0.01. And every time we have something converging or approaching zero, that means generalization is happening. So if we don't have this, we cannot ensure learning. And that's the condition that Vapnik defined like a long time ago, 1965 from 1999. That was the period of time. And that's how we define learning, basically, in terms of supervised learning at least. Yeah. So if we have, like, for example, a set of classifiers, let's say we have classifier F1, F2, and Fm, and they've got different empirical risks. I mean, risks in a given sample, could be the training sample, but could also be a test sample. Let's say this is the training sample, just to make it easier to understand for now. So we could have like different empirical risks and different expected risks. Consider this first classifier has, for example, an empirical risk equals to 0.1, 0.0. This other like 0.1, and this guy here like 0.5. If the expected risks here could be like 0.2, 0.15, and this guy 0.52. If we measure generalization, this guy is the one that best generalizes, because generalization means zero in this case. So, I mean, it doesn't matter if we have like the smallest risk as possible. Generalization is not about that. It's about the distance we have in between the empirical and the expected risk. So a part of the good results we've got here, and this would be like 0.19, right? And here would be like 0.05. A part of that, the best result, the best generalization happens with this guy. So besides the generalization, there is something else we must be interested, which is the reduction of the empirical risk. So Vapnik was interested in two conditions, two basic conditions. Ensure the reduction in the empirical risk and ensure generalization at the same time. So if we reduce the empirical risk and at the same time we have this generalization term approaching zero, we learn and have a useful model. What's the basic idea behind that? I'd say this is probably the most important part. It's impossible to measure this guy for real-world problems. If we are considering real-world problems, we just can't measure this guy. Because, I mean, we don't have full access to the joint probability distribution of a real-world problem. Because that would require access to every possible input and every possible output for that problem. So that's the same as if we have like, throwing a die or whatever, that's easier to measure. We can have like the perfect solution. We can compute the expected risk because that's a toy, basically. But if we go to a real world problem with several inputs, and I mean, could be like just a single input, but that input could be real. And if it's on the real line, it's just impossible to have all possibilities, right? So it's just impossible to represent a real world problem and compute the expected risk. And because of that, it is important to compute the generalization and ensure the empirical risk reduces, because that could be a very good estimation for the expected risk. So he decided to use this term to find a good estimation for this guy. An estimation happens in here because this guy I can measure. I have samples. I can have somehow samples. I can build up samples and compute the error, the risk. The risk and the error are the same thing here. So it's how much we miss, basically, in a given sample. And if we ensure that error is somehow useful to represent the behavior for unknown, unseen examples, voila, we have the result, right? We have the final result. We have everything we need. Okay, from that, it's useful, I believe, to define those risks, just to have a better idea how they behave, right? So usually, Vapnik defines risks like this. This expected risk is the same as, this empirical risk is the same as the average risk from 1 to n, given some loss function. And that loss function considers our classifier f being applied on a given input value, a given input example, which should produce a given output, and maybe it doesn't, and that's why we can somehow measure error here. And that's empirical. And the expected is just different. The expected is just the expected value of this loss function in terms of every possible input and out and expected outputs. That's why we don't have like an index here. That's to represent a space, basically. So you've got the whole space, the whole input space, the whole output space. And this loss function could be, for example, a squared error function or a 0-1 loss function. Could be any kind of function you decide to use. So on top of that, the next step, I will define how Vapnik decided to, what kind of tools he had to use and solve this problem. Because that was basically the problem. If you guys have questions, yeah, just start. Maybe that's just the beginning, right? That's just the goal. Okay, my goal, actually not just mine, but Vapnik's goal was to reduce this guy here, because if I reduce the generalization, I have somehow a good estimation for the expected risk. I know how my model will behave in real-world conditions, even if I just have access to some sort of sample. Even if I have access to a given sample and measure the error in that sample, right? In addition, I also have somehow to reduce this guy. Because if I don't reduce this guy in conjunction with this guy approaching 0, it's just impossible to learn, because I could have like the best, let's say it's possible to generalize with a coin, for example. Because if I flip a coin and the average error is like 0.5, in practice, in real world conditions, is gonna be 0.52. It generalizes, but it doesn't learn because I don't have like a good result. At the end of the day, the result is like terrible, right? Maybe I could go to the next. From that,